Hey there, are you a nerd like me? Too bad. You're coming with me anyways. Beep. Oh. Beep. So today's question is, why do we use base 10? Alright, I have a great explanation for that. Alright, so I think I know what you're gonna ask. What are bases? And I have a great explanation. Hold up, let me just find wiki real quick. Hold up. And I got it. A base is a natural number b whose power is b multiplied by itself some number of times, are specifically designated within a numerical system. The term is not equivalent to radix, as it applies to all numerical notation systems, not just positional ones with a radix. In most systems of spoken numbers, some systems have two bases. A smaller subbase and a larger base. An example is Roman numerals, which are organized by fives. V equals 5, L equals 50, Z equals 500, the subbase, and tens. X equals 10, C equals 100, and M equals 100, the base. Or in layman's terms, a base, you take a number, that's how many digits there are in the base, and then the number, you take the number that's in that position, you multiply it by the base to a certain power. So here's a beautiful example of this. Let's take base 10. Base 10 is the system we use as humans. I mean, you know how to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. And the base has 10 digits, and each number is multiplied to 10 to a certain power. Now, let's take our base 12. Since we have 12 digits, we need to make two new digits. Dec, which is this, and L, which is this. I like this one better. Yeah, that one. So base 12, we can basically use information from base 10 or base 12. We got 12 digits, and the number gets multiplied by 12 to a power of another number. It's that easy. So the Mayans, they use circles for zeros, dots for ones, and as a subbase, strokes for 5. So you can kind of imagine what 20 would be like. It'd be a dot, then a circle, because dot is worth 1. So 20 to the power of 1 is 20. 1 times 20 is 20. And since 0 times... Alright, hold on. Let's look at 20 to 0 first. That is 1. 0 times 1 is 0. So yeah, you can kind of imagine how the Mayans did it. And then we go to the Babylonians, which they use base 60. And this was done by ones being boomerangs, kind of, I guess, and then 10s being like huts, as 10s are our subbase, as 60 is our final. And for some reason, and this goes on to the next base 2, which the Egyptians use, the Babylonians don't have a representation for 0. I've tried researching, can't find it. So going into our next base, we have the Egyptians, which kind of didn't use a base, kind of did. You see, they kind of followed suit of the Chinese, in which every x times 10 to the power of y had a different symbol. So 1, 2, 3, 4, 5, 6, 7, 8, 9 all had a different symbol, but 10, 20, 30, 40, 50, 60, 70, 80, and 90 all had different symbols too, and this goes on and on and on. So now that we've discussed what bases are, let's look at the pros and cons between base 10 and other bases. So first, it was actually based on human anatomy, as we have 10 fingers. And I guess a secondary reason, it's not the exact reason why we use base 10, but it's also easy for kids to memorize their multiplication tables for around 7 of them. 7 to 8, I think. It could differ depending on what you think, but here's what I think are the easiest. 1, 2, 3, 4, 5, 9, 10, and 11, as they all have distinct patterns that can easily be memorized. And now we get to irrational numbers. Think of pi, Euler's constant. These get really hard. So let's think of pi. 3.141592653589793238462. It can go on and on forever without an end. And things like base pi, of course, pi to the first is pi. So pi would basically be 1, 0 here. And now let's look at our base 10 again. It'd be 3.14159265355. That is when it's truncated. Instead of the 5 at the end, it'd be a 6 if it were rounded, because after the 5, there's an 8. Alright, so after that, let's now discuss base 12, which is actually argued to be, with base 6, a more useful system than base 10. Let's first look at the multiplication. Basically, 1, 2, 3, 4, 6, 8, 9, dec L, and 1, 0, which is do here, is super easy to memorize, with only 5 and 7 being difficult. You could also make the very, very superly duperly good argument about base 12, like this guy over here.
Oh, how can you count on your fingers?
Alright, just, you see that door there? Just leave. Oh, okay. The main reason why I say base 12 is easier than base 10 is because you can also count your fingers up to 144, which in base 12 is either grow or grows, just depending on how you want to do it. Look, alright, so I have my fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, dec, L, do. And then you can just use your other fingers to hold the does. Like, see? That, since it's on the first one, so do, 2 do, 3 do, 4 do, 5 do, 6 do, 7 do, 8 grow, 9 do, dec do, L do, 1 grow. See how easy that is? Now after that rambling about base 12, I am now going to get on to other bases. Let's take binary, base 2. Can you tell me what this number is right here? Yeah, that is 124. If you got that, great job. If you didn't, it's okay, because it's super hard to read out all those digits super fast. And that is a big problem with small bases. Let's look on the flip side and what big bases are. Think of stuff like base 60, base 75, base 100. Oh, they're super short to read. Yeah, but my question is, can you memorize all 100 digits in base 100? Yeah, I don't really think you can too easily. Nice try. So, now after these regular bases, let's go into these irregular bases.
Whoa, dude, do you mean it's not just regular bases?
Okay, I'll be seeing myself out. Thanks. Anyways, we're going to be talking about these irregular...
Okay, so what are we going to be talking about?
Oh, so we're going to be talking about... Anyways, numero uno, irregular bases. And what I mean by this fractions and irrational numbers. Let's take base 1/2. It is basically the reverse of base 2. And no, I know someone out there thinks it's -2. It is not. So basically, what base 1/2 is, it is every number after the decimal, like to the right, gets larger, and vice versa. Now let's get into negatives. So let's think about base -4 and the powers of -4. -4 to the power of 1 is -4, but -4 to the power of 2 is 16. So over here, well, right here, this is how you count. And actually, let's get back into irrationals. Radical base 2, or square root base 2. As 2 is now 100 because square root of 2 times square root of 2 is 2. Quarter imaginary and or complex bases. They seem really scary, but let's break it down. So it is x times I plus y. What is I equal to? I is basically our stand-in for the square root of -1, which mathematicians basically, it's just a fill-in. And it makes things possible in the world of math that usually wouldn't be possible if we didn't have a number for it. And let's see how we count in base 2i. Here it is. Do you notice something? If you think back to base -4, you will see a pattern where zeros fill in gaps in base 2i. Now, complex is honestly way out of the question for me, and I don't know much about it, but you can research it yourself. And there's also other base types like bijective and balanced. Basically, these are kind of modifiers, if you want to say. Let me give what they do. So balanced. And so let's take balanced base 3. Instead of having 2 as a digit, we have -1, which is t. So let's count to 9. Alright, so let's count. We got 0, 1, and then 1t. T is a -1, and a 1 in the tens place is 3. 3 minus 1 is 2. Then we got 1, 0. And then 4. That's just 1. Fooled you. And now I haven't fooled you because we're getting on the 5. Since we don't have a 2, we gotta start looking at the 100s place. So, we got 1tt. T and t is -4, and 1 in the 100th place is 9. So, 9 minus 4 is 5. Then 1t0, 1 in the 100s place, which is 9. And then we have a t in the tens place, so that's -3. Then we have nothing, so yeah, -3 plus 9 is 6. And then 1t1 is 7. And then I think you know how it works. I think you can get it on from there. 10t, then a 100. So now we got bijective, which it's basically removing 0 and putting the base number in. So let me show base bijective 4, or bijective base 4 is another way to say it. And we have our picture right here. Yeah, look at that. It's confusing. That's a 1 to 21. But I think you can kind of comprehend if you just follow the other terminology that we've used previously. Congrats, my pupil. Now you know what base 10 is and other bases are. Alright, so let's answer our burning question. Why did we use base 10? So here are your choices. A, yes. B, no. C, none of these answers are correct. D, we've previously discussed this. Or E, there is no answer. Alright, so the answer was D. We have previously discussed this, which was human anatomy as 10 fingers. 10 beautiful fingers. And why didn't we use other bases? They were either A, too confusing, like irrational bases, or complex, or quarter imaginary, or even negative for effect. B, they were too small. C, they were too big. And D, our new reason, they are prime. So let me explain what prime numbers are. It's basically a number, which is represented by a p, that is divisible by 1 and p. So yeah, try and convert something like 1/37 to something like binary. The conversion is not too easy. So to summarize, we have used base 10 because it is easy to memorize, and our human anatomy allows for our fingers to be used for counting. And other reasons is because A, 10 is not a prime number. B, it is not something like irrational, negative, quarter imaginary, or complex base. C, it's not too big where you have to memorize several digits, like 100. And D, it is also not too small where some of the big numbers are too hard to read. That's going to be the end of today's video. Bye. I really hope I pass.